Yeah. It will be on the test. Cofactor versus coenzyme. Tell somebody else what a cofactor is versus a coenzyme.
Cofactors are non-protein compounds, and they biological activity.
Coenzyme is subgroups.
Damn, I totally got it wrong too when I took it.
Okay, not a lot of time, right? So if it's just a metal, cofactor. If it's got any organic molecules in it, coenzyme. Even if it's got a metal with that, it's the coenzyme. Okay, so a lot of your vitamins are coenzymes, okay? And the green there, not specifically mattering, it's just that's the one that's not a vitamin on the list. Okay, everything else is vitamins. Okay. Lipoate, that's just a fatty acid, okay? Cool. Buchner, you know who that guy was?
He was the
Talked about him.
yeast.
The wine,
Yeast.
the yeast.
The yeast guy.
Yeah.
The yeast guy. Also the Buchner funnel, the one you use in that? Yeah, same guy. Cool.
He's only on the funnel.
What a Wilbur's man.
Cool. Urease, crystallization. Okay, cool. Haldane, a treatise. That is boring.
Just step on his grave.
Yeah.
Just do it.
Good.
Jump.
Yeah, cool. Enzymes are specific. That's cool. There are 7 classes of enzymes. Do you need to know those?
Yes.
We also need to know the order that they're in, is that right? No? Okay.
But if I say, now here's one that will get you, okay? If I say something is a transferase, it's doing what?
Transferring
functional
group.
functional.
Okay, what if I'm an isomerase?
Rearranging the
You're
bonds.
transferring it to itself. if that
I
makes
could
sense.
transfer an functional group to myself and I'm an isomerase, but if I'm transferring from another molecule to, that gets tricky, right? But so pay attention to what's going on, to put something together, to pull something out, don't get confused, right? Ligand, lyase, cutting up. Translocases just started, like that wasn't even a classification like 2 years ago. It's new. I still struggle with it. And we always talked about these, we just didn't call them that. So when I'm moving something across the membrane, translocase. We just call those transporters. Like, but does it take energy to get something across the membrane? And if it lowers the energy to do that, well, that's kind of an enzyme. Okay. So they probably talked all about the lock and key mechanism, how it's totally false, right? What?
Yeah, we didn't talk about the falsehood of it.
What?
So,
Okay, so big aha moment. You heard lock and key for all your life. If I have a lock and my key, what's it gonna do? It's gonna fit it where?
In the keyhole.
Exactly. And it's gonna be
It's not
1
the
fit.
first thing.
Is that right?
no,
No.
Wait, you talked about the stick ace model, right?
I don't think we did.
He grabbed a marker and said it has to be like Jasper.
Okay, we'll get to it. Okay, so secret, right, is that an enzyme, when it binds to the substrate, it's changing the shape of the protein. And that's then fitting the key. Not the perfect, the other way. They do match, they just don't match the way you think they do. It has to match with the interactions that happen. If it's a perfect match, which we're going to get to in a second with the stick ace model, it doesn't even work. All it does is bind. It doesn't become an enzyme. Delta G itself, enzyme can change the rate I get to it, but it doesn't change the delta. Okay, we just talked about that. You just had a quiz on that. You get all that stuff. That's cool. These numbers, you guys, it's not like crucial that you like do everything, but what do you notice about this pattern?
5.7 kilojoules.
5.7 kilojoules. Okay, so if this is 5.7 kilojoules either way, what are we talking about here with the K equilibrium? What is happening? This is 10 times faster. This is 100 times faster. This is 1,000 times. This is talking about increasing the rate the reaction happens to get to its equilibrium. And essentially, if I give it just 5.7 kilojoules of energy, what am I changing? An order of magnitude. So then we turn around and we look at that, and we do this whole, and this formula right here, you should know, okay? But this one over here, I don't care if you know this one, okay? But I have you go through this rearrangement to do that, so you can end up solving the same thing that says how much energy does it take to go 10 times faster, okay? But here's the message that I really want to get, so that you get an idea. When we want to uncover a mechanism of a reaction, wouldn't it be nice if I knew how many amino acids it was interacting with? Where the substrate is interacting with the enzyme, how many weak interactions? Well, if I know how much faster it goes, oh, it goes 100 times faster, it goes 10,000 times faster, or it goes 100,000. I could get a number based on that 5.7 and know how much faster it's going. So it turns out that if it went, in reality, 57 kilojoules faster, and then I know that a weak London dispersion is about 4 kilojoules of energy, van der Waals force. If I have a hydrogen bond, it's about 30 kilojoules of when the interaction happens. That's how much energy is being released. Now, we just had a great conversation just a second ago before class, Connor and I, and we were talking about the fact that when something comes together and a bond is formed, or a weak electrostatic intermolecular force happening, I'm actually releasing energy. And when it comes apart, it's going to take energy. Now, there is a reality that some of you still question it. And the aha moment you should have is the same one that Connor and I talked about. What would happen if a molecule, every time it broke it apart, it released energy? It would mean that it would then take energy to assemble every molecule in the universe. And it would mean that once it was assembled, what would it want to spontaneously do? So would there be any molecules in the universe? There wouldn't be. But what did you hear? You heard, well, when I have ATP, I did the same class as you did, okay? When I have ATP and I break the bond, I release all. You were forming bonds that you weren't talking about. You don't get the energy for breaking ATP apart. You get it from making new bonds that you're forming, even in ATP hydrolysis. Why didn't they just say that the whole time? I don't know. They could take my class, okay? But I'm telling you, that's the way it works. So, but these bonds, we're just going to take an average and say it's 15. That it's not real. It's one or the other, right? But if I decide 57 or 60 by 15, we get like 4 week bonding events. So I could increase it in this factor by what? 10 to the 10th faster reaction by like 4 week bonding events. Is that like realistic? Look how this is normal enzyme rates. Whoa, that's like 4 intermolecular forces interacting with it could give me all the energy I needed to make it go like a bazillion times faster. That's where the energy's coming from. That's what's lowering the activation energy. God's like an awesome chemist, isn't he? He's cool. He knows what he's doing, and he did that, okay? So, yes, some problems. Now, in lab, Lee, yesterday, you guys purified some chloroplasts, right? And then you showed how when they do photosynthesis, they produce a high energy molecule, and that reacted with a substrate to change the color of it. And that was a cool reaction in itself. But then you played around with the temperature, and what happens if the temperature gets too hot to enzymes?
Doesn't work, or it slows down a lot.
Yeah, I can destroy it. I cook it like an egg, right? It dies, and that's totally achievable. So it turns out that enzymes are not like other catalysts. I can't just keep increasing the temperature and it keeps going faster and faster, because I'll destroy it. Okay, so pH is a big deal, temperature is a big deal with that. And pH obviously a big deal for what reason? What do you know about pH changes for proteins?
Protonation, deprotonation.
Protonation, deprotonation, which forms salt bridges or break salt bridges, which can lead to even protein aggregation, meaning it makes clumps and falls out of solution. Yeah, that's a big deal, right? So pH matters. All right. This is describing also how these same enzymes lower the energy. You know where the energy came from, but what is it doing? Well, this is actually pictorially telling you what that just said. Now, did you guys look at this slide?
I don't think so.
Okay. I have two substrates, right? I put the two substrates together, and they will actually spontaneously do this awesome reaction. We're going to call this rate order 1, okay? But if I take these same reactive groups and I make it on the same molecule, but the molecule can twist and turn, so it's not always in the right orientation, but they're on the same molecule, I increase it by a factor of 5. That's huge. That's a big deal, just because now they don't have to worry about finding each other. They're already attached to each other. They just have to do what now? Get in the right orientation. But what if I lock the orientation in place? I jump up even further. Do enzymes do that? Mm-hmm. Yeah, they find part 1, part 2, put them together, shove them together, get them the right orientation. That's what an enzyme's doing. Tell your neighbor you understood what I just said.
Understood.
It's like neutral.
I guess
Enzymes are neutral. Except for that.
Let's read these together. By the way, if I read them, you'll actually understand them less. So let's just read them together. I'm reading them, you're reading them too. Okay. Everybody good? Okay. I put green on it. That means it must be important. It must be tied to study guide. This is the stick ace model that I just mentioned 2 seconds ago. It was the same one he was talking about, markers. This is the stick ace model. Here's the thing. If I had some awesome ruler here, which I wish I did and we used to, and then somebody actually broke it, the very thing that I was using as the demo you should do. But it turns out that if I wanted to break this in half, it's going to be a lot easier for me to step here and snap it in half, right? As I push in it. But what would happen if I put this flat on the floor and I try to snap on it? It's going to be really hard to snap that in half, right? Same problem right here with a stick ace model. What if the enzyme, you're good. What if the enzyme itself matches perfectly with the substrate?
nothing will happen.
It's going to bind really well, but is it going to go to product? Not ever. The substrate doesn't match the active site. but it can force, because there's interactions with it, force it into the transition state, which is the point where it could go back to substrate or onto product, and it can get it to that point so it's able to fall either way. And it's stabilizing it in that. So the stick-ace model is talking about that principle. So when you see questions on the exam talking about this, please do not put down on the exam that you think that it binds the substrate better than the transition state, right? Because it binds, but does it have to bind the substrate? Yes, but it can't match it perfectly if no reaction happens. It would just be a ligand for that one, okay? All of this explaining the very same thing, okay? Okay, lots of green, we're going forward. Yep, fantastic. Part of glycolysis, full reaction, mechanism, showing you the mechanism, arrow pushing. What's the secret here? The charge state matters, right? Does this look like arrow pushing mechanisms that you learned in OChem? Yeah, it does. What becomes more complicated? More to draw. Okay? Well, it's just an arrow pushing mechanism, okay? That's all we're looking at. Now, you don't need to learn that one, okay? There are 3 types of catalytic mechanisms that we will highlight in our 481. We will be highlighting acid-base catalysis, covalent catalysis, and metal ion catalysis. Acid-base catalysis is fairly straightforward. It just says what? I'm getting a proton or donating a proton or receiving a proton. That's acid-base, okay?
So is that the enzyme acting as an acid or base?
Uh-huh.
Okay.
Covalent catalysis, if it's really happening that at some point during the reaction, the actual substrate covalently attaches to the enzyme, covalent catalysis. Metal ion catalysis is using redox as doing either redox cofactors or pKa shifters, something where I'm stabilizing it with the metal ions. And I prefer to think about it as redox ones, but I'm going to show you examples where that's not the case. All 3 of those are the ones that are there. Acid-base is far the most common. Covalent catalysis happens. Could I have multiple of these on the same reaction? The answer is yes.
Yes.
Okay. So, what amino acids could do acid-base catalysis? There's a list of them. Why don't you name the right ones to your neighbor? Which ones could do acid-base catalysis?
Aspartame.
It's going to be a ring
No. It could be.
There are 8 of them, by the way.
Is there anything you could, right? Because they both have different hydrogen bonds.
Well, it has a.
So yeah, it would.
All the bottom 4.
Lysine.
Would be like this.
Yeah, lysine, tyrosine, histidine,
Yeah,
So like arginine, tyrosine, lysine. It's just like they're single.
What about these guys?
Yes.
That makes perfect sense, right? Okay. All right. What about these guys?
Oh, yeah. Keep it movies.
Oh yeah.
Yeah, that makes sense. Hydroxyl?
Oh, I missed
yeah.
3.
Yeah, okay. Yeah. Those are your groups. Those are the 8 you're looking for. So, you're looking at it going, I learned Ricky Chet and serine, I didn't learn a pKa for that mattered. It's because we didn't teach it to you, but we're going to. Go ahead.
Why does serine work on alpha?
That's actually a great question. It's position, access, angle of attack, and that's all I got.
So, I mean, should we-
I don't know 100% because I don't get to talk to them. These awesome molecules, but yeah, it's just it is just restricted the position on it. Yeah, and sometimes we'll act like it's somehow accessible, but most of the time it's just not. So it's very different in the way its reactivity works out. Okay. I wouldn't need to have a catalysis reaction to do acid base and have a catalytic if it turns out that what happens here. If protons were transferred to the intermediate and the water faster than the immediate breaks down to the reactants, it would happen without me. No enzyme would be required. So that's the point there. It's not crucial if you get that one right, but it's important to understand that. Okay, we already talked about covalent catalysis, metal ion catalysis bound to the enzyme, interaction with the substrate, participation in oxidation reaction. Okay, so chymotrypsin is the one that you will be memorizing a gory mechanism for and kicking back for points on the test on the write-on. It's a protease. A protease is an enzyme that chops up what? Proteins, okay? So chymotrypsin is one of them that lives in your digestive tract. It happens to live in the lower digestive tract, and it's activated by trypsin, which also lives there. It reacts with aromatic amino acids. Why don't you name those aromatic amino acids to your neighbor and tell them how
Tyrosine,
smart?
valine,
Histidine.
histidine, proline.
For your
Because the entire ring isn't.
You rock, you got this, right? This is no problem. Some of you on your write-on revealed to me something that you still are working on those amino acids. Please get it figured out. You're gonna have to use them again. You gotta know these. It doesn't go away. It keeps beating you up. Get them down. I'm sorry. Like the stuff that dreams are made out of. Bad dreams sometimes and good dreams otherwise. Rewards for those who know it. Yeah. I could affect it by the concentration of the enzyme, by the concentration of the substrate, by effectors, okay, and by temperature. Does temperature really come into play? Yes. That's why you refrigerate stuff, right? Or freeze stuff. It matters, right? But for the most part, you gotta be careful with what you're doing with temperature limits. These guys right here, Michaelis Menten, are the pioneers of what we classically call Michaelis-Menten kinetics, okay? That you get to learn. Let me tell you just a brief, why would we care about enzymes and understanding what enzymes are? God is a better chemist than we are, okay? So currently on Earth, talking with a student who took this previously, just the other day, in fact, just yesterday, and they were talking about just all the cool things they're coming to understand about this guy by the name of Haber. Haber process costs 1 to 2% of the world's energy annually. It's a big hog of energy. We have to go to high temperatures and high pressures to get the Haber process. What does the Haber process do? Does anyone know?
Doesn't it turn nitrogen gas into
That
ammonia?
N3 bond of N2, that 3 triple bonds, that takes a tremendous amount of energy to break it apart. And we want to break it down so we can make it into ammonia, so that plants grow. One crazy thing out in the universe, it turns out that 1/3 of the Earth's population currently is alive strictly because of that Haber process right there. In fact, 1/3 of your amino acids in your body and your nucleic acids in your body are because of that process. We could take the current 9 billion people on Earth and scratch that down to 6 billion if we didn't have that process. The old Saturday's Warrior, they sang about the zero population. Yeah, we are talking about a people that want to believe that there's a limit to how many people can be on Earth, and so you shouldn't have children. By the way, that lie still perpetuates today, and I can't be happy if I have children too, right? Because I could never go on my awesome trip. I have 9 children. It just sometimes delays things, right? You guys, God revealed knowledge, such as the Hopper process, and He can reveal other knowledge that He has that we don't know to handle a population that's vastly greater than what we are. Multiply and replenish the earth, that you may have joy and rejoice in your posterity, is written in Scripture in multiple locations, starting from the days of Adam, and has never been revoked. It's up to you and your spouse, as you marry, how many children you have. I will not dictate that. But it's not just you and your spouse. There's one other person in that equation. It's God. And I promise you that there is joy in having families. No greater joy. Power to create life and destroy life. God reserves one for Himself. The other one He lets us share it. Awesome. Wouldn't it be awesome if we could do this? God does it at what? Room temperature. All life on Earth exists because of it. God's had it around for, well, a long time. What about photosynthesis? Wouldn't that be so cool? If we could like split hydrogen and oxygen and we could like have clean burning combustion. I know it's explosive, but what would it be so cool? I take some hydrogen and I burn it in the presence of oxygen, get this tremendous amount of energy, and what happens? What's the waste product?
Water.
And then what do? I just turn around and do it again and again and again and again. That's awesome. We should do that. Oh, God knows how to do that. It's part of us. Like, just shine some sunlight down. It's all cool. We can't do that, you guys. But who could we learn from? Him. He's the best chemist we know, and he's better than we are. He's smarter than we are, and we can learn from him. Now, I'll get off my soapbox. By the way, this is new knowledge of how the Bosch-Haber process could be done. April of 2023, we found that we have this cool little catalyst that we could take some iron oxide and we could have some compressed air and some ammonia. We can rain down and we can make ammonia. Yeah. We have some Teflon hanging out with it too. Yeah. We did it. We just don't know how to upgrade it yet. Just micro droplets, a little aspiration. We could do this. Figure out how to do that better. We'll say today. Michaelis-Menten equation. First principle you need to understand. We got 10 minutes, 11 minutes, okay? We'll use every second and then we'll wish we had 10 more. Sorry to get off track. This is Michaelis-Menten equation. You're going to need to memorize it. Check. You will put it on the exam. You will write it. You will need to know that, okay? You don't do it, you miss points. In understanding it, you will need to understand the first principle of why we care about what's called the steady state assumption. I used to derive the Michaelis-Menten equation. It does it in the book. Go knock yourself out. I found that when I went through it, it was really impressive to students, but it did nothing for them. So I'm saving you a day of time. Okay? Sucrose plus water going to glucose and fructose. This was the reaction with an enzyme named invertase that breaks down. Yeah, sucrose. Okay? And steady state assumption will go with first this. This is the overall reaction. I've got an enzyme and I've got a substrate. There's a rate where the enzyme and substrate come together. There's also a rate that would happen if they were to go apart again. if they're together, the enzyme can do what it needs to do to allow it to go back to enzyme and now product in the forward direction. But all enzymes are reversible. There are many instances where you see biologically they don't go in reverse. And there's many reasons for that. And so we'll call them irreversible reactions. And you'll spend on next semester a whole bunch of time talking about that. But all are theoretically reversible. But if CO2 is formed and it bubbles away, it's really hard to get it back, right? So K2 is the reverse rate where they go backwards, okay? So there's this equation. It turns out that in practicality, we do the measurement when it is at steady state, which is also done early on in the reaction before I have a substantial amount of product. Which means that we're going to ignore the K negative 2 because there's no product available to be going backwards. We're just going to act like it didn't happen yet, okay? This is steady state approximation. Let's look at it. The enzyme substrate concentration, that's this right here, this orange line, early on reaches a point where it is what?
Steady state.
It's not moving. Its rate, its concentration of the enzyme substrate concentration is constant. This is constant. That is steady state. Now that's where they come together, right? But what's going to happen to that once it comes together? It's either going to go back to enzyme and substrate or forward to enzyme and product, okay? And then there's a rate that it's forming. And so those three things, because we're early on, before we have a lot of product, those things are the ones at play. And so I've got two that come apart. One's going to product or one's just going backwards. And one that's the rate coming together. And as long as those rates are equal, I'm at steady state. Okay? Essentially, the K1 rate versus the K negative 1 and K2 rates must be equal. Now, what happens that this stops being steady? Substrate runs out. When substrate runs out, it's like running out of gas. It starts to sputter. It has a hard time finding the substrate, so it can't load it up. The enzyme doesn't go slower there. It's not going slower. It's just having a hard time finding the substrate. Yeah.
So I have a question. When you're at that state, is it?
Does product now care? Yes.
So you're.
Yeah, I'm
rate of
showing you
K2
the
changes.
principle, but we do it very early on. So it turns out that this build-up state takes usually microseconds. This lasts for a little while, and we read it on our data points early on. So, but that's what steady state was. Does everybody kind of feel like you understand steady state?
Wait, so is the important part of steady state that the enzyme substrate complex formation and breakdown are equal, or is it that there's not a buildup of product? Because that one side is K1 and K negative 1, the other side is K2 and K negative.
Yeah, so we will take it so early on that it won't matter. We'll take it before we have a substantial amount of product. So that won't matter, which also means that we're taking it before we ran out of substrate.
Okay, so it's K1 and so it's K2 and K negative 2. And
Equaling
the fact
to
that we're
K1, yeah,
K negative 2.
yeah.
That's the steady state zone?
That's really what steady state's talking about, and that's done early on, okay? Now, that means we have three rate constants that we're interested in, and when we combine all three of those as if the reaction were just one whole, that's called our Km. And so you need to know what a Km is, so much that what? I put green boxes around it and say you should know that. Now, coincidentally, memorize this, this is the Michaelis-Menten constant. Now, there's some weird artifacts that are also important to connect. And this one comes back to bite people on the exam. So it's in green, and it's not going to get you. It might get your neighbor, but it won't get you. K2 is what rate? It's the rate of product formation. If K2 is very, very small compared to K negative 1, now if I were drawing that on a graph, what would I be drawing? Okay, we're talking about a graph here, and what I'm saying is this is K1, and this is K2, sorry, K to the negative 1, and then this is K2, and this would be K to the negative 2. Wait a second. K2 here,
Oh no, K2 there.
right here, is really small. Is this small? The answer is yes, K2 small. Why did I label this K2 but this is big?
And you're talking about the rate, the slope?
This is the energy right here, but the rate, if it's really slow,
It requires a lot of energy.
it requires a lot of energy to get over it. But if it's really fast,
Doesn't require much.
yeah. So they're inversely proportional when we talked about the height here versus that. But when K2 is much, much smaller than K1, then what we're talking about is that when I write these three equations, and I'm saying, hey, I've got K1 plus K2, sorry, K negative 1 and K2 on the top, and then K1 on the bottom. And this one's so small, we're going to treat it as if it were effectively 0. It's not 0, but we're treating it as if effectively 0. And when you learned this was what?
It's KD.
That is KD, the same KD you learned about with ligands. That's the affinity for the ligand, which now becomes the affinity for the substrate, meaning that as long as this one's the slow step, the rate determining step, what will I get building up here is the enzyme substrate. It will build up because this is going there and then it's trying to come apart, but it will eventually build up enough concentration that I will get to product. Go ahead.
At what point is K2 negligible? Like how much smaller?
Yeah, so ultimately, almost all the reactions that we'll look at, this is what it will look like. But we'll do an activity where we'll show you several other plots that could exist, and some are feasible and some are not. But for all intents and purposes, this is what real enzymes typically look like that do Michaelis-Menten equations. So we essentially associate the Km with the KD, meaning the affinity for the substrate. Okay, all right. This is the derivation that I told you I'd skip. Wasn't that awesome? Way to go. You actually saw this math before. Whether you got it before when they did it with ligands, I don't know. But if I have a Vmax, and I have 1/2 of the Vmax is the velocity. So I'm essentially saying that my velocity over here, which was my Michaelis-Menten, V0 equals Vmax over substrate plus this. If this is 1/2 of Vmax, whatever the velocity is, then I can plug in some cool numbers here, which says I can cancel out the Vmax, and now I have 1/2 is equal to substrate Km, right? So then what could I do? Well, multiply everything by 2, right? Okay, that means I now have Km plus substrate equals 2 substrates. And then what would I do? Well, move this to the other side. That means that Km equals the substrate concentration, which is why when you make a plot, 1/2 of the Vmax, which is this position, the maximum velocity that it will obtain, 1/2 of it is the Km, which is read in the substrate concentration. Now, we are at time. This is what I intended to do. I want you to know this right here.
So get to that one.
Look at this in your notes. We'll come back and go over it again, but look at this in your notes so you know what it is. We'll go through this. I wasn't sure where they got to, and it looks like they hadn't. That's why I went slowly over some of the first stuff. But we want to be at the point where you at least know what this fine weaver bird spot is. We'll come back and review it, but you should know that by Friday, okay? So that we can go a little bit faster so we can catch you back up.
Where are you going?
Okay? Just look at what's going on and we'll answer questions on Friday.